Okay, this is the third video on Chapter 9, the bonding chapter. I had just covered ionic bonding. There's two more comments I want to make about ionic bonding before I move on to the second type of bonding, which I'll cover here, which is metallic bonding. So, again, I'd indicated that ionic compounds tend to be quite hard but also brittle. And that is because if you look at their lattice structure, they're a very neatly organized combination of cations, positively charged cations and negatively charged anions that are lined up so that the opposite charges are as adjacent as possible. Again, this is it happens, it exists in 3 dimensions, but I'm drawing it in 2 dimensions here. I had mentioned why they're brittle and hard. A couple of things I want to, a couple other aspects to ionic compounds is that in solid form, they do not conduct electricity very well, and this kind of makes sense because even though there are ions, the ions are rigidly bound in this lattice, and so if you were to put a electric field between the two, there aren't really free electrons to flow, which would be needed to conduct electricity. So in solid form, ionic compounds are not electrically conductive. However, in molten form, when you melt them, it turns out, or even dissolve them in, let's say, in water, in those two scenarios, the ions are indeed loose and therefore can flow to or from an electrode of the opposite charge. So again, in this case, in a molten case, and none of these videos are really talked about solids versus liquids much, but in a molten form, these cations, instead of them being arranged in a nice, tight, organized lattice, they're actually a bit decoupled from their anions. And of course, so they form this very loose arrangement in the liquid state, still attracting each other, but they're much freer to move. So that's why molten ionic compounds conduct electricity. The other thing, though, is that since there's such high lattice energy in the ionic compounds, it takes quite a bit of energy to melt them, and it takes even more energy to boil them. And so what you'll find in ionic compounds is that their melting points are quite high, and their boiling points are also quite high. And that's again because of the strong lattice energy. It takes quite a bit of energy to convert this form into an energy where the ions are less organized and have less close proximity to their opposite ions. Okay. Rigid, brittle, hard, high melting, boiling, and conductive. Okay, good. I think that's all I want to talk about ionic. Now I want to kind of compare this a bit to the metallic bonds, and that's the second type of bond that I'll cover. So metallic bonds are essentially the bonding that occurs when you take a metal. Now I'm not talking about an ionic metal. I'm talking about a neutral metal. Well, let's just take one like iron. Okay. All right. So in iron's case, let me draw the Lewis dot for iron. It is essentially the arrangement of argon, but it has is that 4s? I think so, right? Yeah. It has 2 4s and 6 Ds, 1, 2, 3, 4, 5, 6, yeah. And 3 D. I'm going to say 6, but I think it is 6, isn't it? Yeah. There's a 5. Yeah, I guess it's 6. Okay. We won't go there. We talked about this when we were talking about orbitals before. So this is iron. When iron metal, or say iron metal exists as a solid, in that solid, what you actually have is now I'll erase this. But remember all those electrons we had. We actually had 8 valence electrons there, where 6 of them were in the D state. What you have are iron atoms arranged in a nice little lattice here. But the dots that I'm showing, these big circles that I'm showing, are essentially the, if you look at this, it's basically the iron nucleus and its inner, meaning non-valence electrons. Okay, so all those form a little pattern here, and of course they're inherently sort of positively charged. Well, they are positively charged because when I'm drawing them is without their valence electrons. But their valence electrons then kind of exist. They're pooled throughout this solid lattice that's formed, and they're kind of everywhere. But they're not. They don't really have a fixed affinity to any one atom. In fact, the book calls it pool. The valence electrons are pooled, and they're pooled across they're across all the atoms essentially. Okay, so this is how they're able to lower their energy by still having that positive and negative affinity with each other. But the difference here is that in metals, the electrons are free to flow in an electric current. So metals tend to conduct electricity very well. They also tend to conduct heat very well as well. The other interesting thing, especially as comparing with ionic compounds, is that generally speaking, the melting point for metals is not as high as you'd think. In fact, I wouldn't call it low. I mean, you look at some metals and it's definitely not a low melting point, but it's actually not really all that high either. Now, the boiling point is different. The boiling point is really, really high for metals. But the melting point, I would call moderate. And the reason why, as compared to ionic compounds where melting point is actually quite high, the reason why it's kind of moderate is that when a metal melts, the situation I'm kind of drawing pretty poorly, is actually fairly similar in a molten, in a liquid form. In that, in a liquid form, you've got these nucleuses, the positively charged parts of the iron atom that are floating around, and you have essentially the pooled electrons are still kind of pooled. That's how I describe it. Is it in the metal, they're pooled across all the atoms in the lattice, and in the molten form, they're also kind of still pooled in the mix of nuclei. Okay, so for that reason, it doesn't take an enormous amount, an exorbitant amount of energy to melt, to turn into liquid the metals. Now, different story when you talk about boiling. When you actually are talking about boiling a metal, the boiling points are really, really high because you can boil them. This kind of soup, this pool of nuclei and pooled valence electrons no longer exists. When you get them in the vapor state, they actually have to exist as gaseous atoms, and so this pooling effect is no longer present. So what you see in metals is that there's a somewhat lower than expected melting point, and also a somewhat higher than expected boiling point. The key example, and they mention in the text, is a metal called gallium, which will actually melt in your hand. It melts at like 30 degrees Celsius. So, 90 some odd degrees Fahrenheit. You put it in your hand, and it'll actually melt into a little pool of metal. But the boiling point is ridiculously high, 2,000 degrees, 2,400 C, something like that. So that's one of the characteristics of metals. The other thing I want to mention about metals is that unlike ionic compounds, many of them are fairly malleable, meaning when you try to deform them with a force, they don't resist it as much as ionic compounds, and when they do resist it, they don't resist it by cracking, by fracturing, like I drew for ionic. And that kind of makes sense because the pattern isn't the same where deforming a metallic part of a lattice doesn't result in that situation where now you've actually aligned two positive particles together or two negative particles together. So therefore they become actually fairly malleable. As you beat it, the pool just kind of moves accordingly, and so you still end up with a stable lattice even though you've deformed it. The classic example of this is gold. I mean, gold is very malleable and quite soft. It doesn't take a lot of force even to deform it. Okay, I think those are the two things I want to talk about, all the things I want to talk about for both ionic and metallic bonding. So I'll end this one.